Um, I'm scared to touch my laptop. Projector wasn't working earlier, so I'll be looking at this kind of an angle there. So welcome to week 2. As I mentioned last week, this is going to be the most challenging topic um, to understand. Some people get this right away. Some people don't. It's fine. Don't feel bad if you don't get it right away. That's normal. The exercises are designed to help, like the labs are designed to help you finish getting it. Um, and now the clicker's not working. Of course it's not. Hang on. If I click on it, there it goes. Okay, so before we talk about normalization, we have to learn something about dependencies. Um, in database design, I'm actually going to close this door. Here, just close the door behind you. So in database design, there's a whole field of mathematics dedicated to database, and it's known as relational algebra. We're not doing relational algebra, so don't worry about that. If you want to sleep, it's a fantastic topic. When I went through school, the textbook we took had a whole chapter on relational algebra. If I needed to take a nap, I just started reading that chapter and I was gone like one page in. It's really dry. This is more about how things are dependent on each other. So with normalization, we want to make sure that, there it goes. We want to just ensure that we understand how things are dependent on each other. Um, so basically how one attribute can define the value of another. So it's usually denoted in a method of X arrow Y. So the attribute on the left side of X is called the determinant. The Y is called the dependent. Determinant would eventually become a primary key potentially. So something determines the value of something else. It's the determinant. So anything to the left of the arrow is a determinant. Everything to the right is dependent values. The functional dependencies can chain. That means a determinant can be dependent as required by other relationships. For example, an order ID determines a customer ID. The customer ID would determine the customer's name. That's why it's called chaining, where one determines the other. So there's 3 properties and 6 kinds of dependencies. I'm going through them so you guys have the technical definitions of it, and then we'll get into the actual normalization part of this lecture. And I've always debated whether I should keep these slides in or not, but it's good to know some of these definitions. All right. So the properties of functional dependencies are as follows. There's reflexivity, man, I can't say that word, and augmentation. So if Y is a subset of X, therefore X determines Y. So X determines student ID and name, Y determines name, therefore student ID name determines name. That's the reflex. It's a, like literally, when they talk about reflexivity, it's like the reflection in a mirror, where if Y is the name, X is student name, therefore student name determines name because X determines Y. So if X determines Y, by default, all the values of X determine the values of Y. Exactly. Because Y is dependent of X, all of its, properties and values become dependent of X. Augmentation is if X determines Y as a valid dependency, then XZ, YZ is also valid. So student ID, name, and course ID. So therefore student ID, course ID would determine name, which determines course ID. So essentially what it's saying here is that if student ID determines the name, and we have a relationship that's student ID and course ID, that will also mean that name is also part of course ID, or course ID is part of name. All right, so we have transitivity. Having a hard time some of these words today. Usually I don't have this much of a heart. It just does not want to come out of my mouth today. Um, if X determines Y and Y determines Z, therefore X determines Z. If X determines Y and Y determines Z, therefore X determines Z. That one's actually probably the easiest of the three to understand. So student ID, department ID, department ID, department name, therefore student ID determines department name. Because this determines this one determines, and then this determines this. Therefore, this to this to this. That's transitivity. Um, it's actually called transitivity because to get to Z, you have to transit through Y. You travel through I to get to Z. But they decide extra letters to make it hard to say. All right, so those are the properties. Now we have the types. Realistically, most of these are going to be fairly forward. So trivial functional dependency. A dependent is always a determinant. If X determines Y, Y is a subset of X. End of story. That's a trivial, as in it's straightforward, it's basic. If X determines Y, therefore Y is a subset of X. End of story. Non-trivial functional dependencies. Um, the dependent is strictly not a subset of the determinant. So if X determines Y and Y is not a subset of X, which is possible. That means that Y has a bunch of its own values, but those values have nothing to do with X. It just happens that X determines its existence. Multi-valued functional dependencies. Um, entities of the dependent set are not dependent on each other. So if A determines B and C, and there's no relationship or dependencies between B and C. So A determines B, A determines C, B and C have nothing to do with each other. So these are multi-valued. A determines a list of values, essentially. But each value in that list have nothing to do with each other. It's that's what it becomes. When you're at first doing the initial data, you might be looking at it as a person with a list of skills. So each of the skills has nothing to do with the other skills, but the person may determine each of the skills. Transitive, that one's straightforward again. If A determines B and B determines C, A determines C. Fully functional dependency, this is actually one of the more important ones. Out of all the verbiage and noise I've been saying, that one's one of the more important ones. An attribute or set of attributes uniquely determines another attribute or set of attributes. So relation R, so now we're not talking about just an out property. If R has attributes X, Y, and Z, and the dependencies are X determines Y and X determines Z. That's fully functional dependent. So Y is fully dependent on X, Z is fully dependent on X. So they're fully functionally dependent. The last one is partial functional dependency. It'll make more sense when I start going through the normalization steps. These are just the definitions that we have to get out of the way. A partial functional dependency is a non-key attribute that depends on part of the composite key instead of the whole key. So relation R has X, Y, Z. X and Y are a composite key. So that means to identify something in R, you have to have both X and Y. And Z is not a non-key attribute. In other words, it doesn't participate as the determinant. However, Z is only determined by X. Therefore, it's a partial dependency because X determines Z, but Y has nothing to do with Z. So it's a partial dependency. When we're talking about normalization in a few moments, that's the first thing we want to get rid of because that's bad. When I go through the normalization steps, I've actually got data on the screen to show you guys. This is the theory side, which is just definitions. Okay, now we got rid of the really gross part of the slides. Now we get into the more normal human sounding things. By the way, those first 5 slides in some courses could be like a week and a half to 2 weeks of lecture, just those topics. In a course where they do the relational algebra as a topic, they will cover all that stuff. This was just the Coles notes. Sorry, the let's call it the Gemini summary version or the ChatGPT summary of what that course would give you. But this is what's actually important is from here on out. The first part's important to just read and roughly understand what's going on. Once you see the examples, that stuff will make more sense. So database normalization is the process of decomposing and organizing entities and attributes that make up a database. All right, so this means that you're going to take large, unwieldy structures of data and you're going to break it down into smaller pieces. That's what they mean by decompose. You're going to take a table with 22 columns and you might turn it into 4 or 5 tables. Decomposition means you're breaking it down. Now, in the real world, decomposition means it's rotting and slowly turning into soil. In database, it means you're just cutting it up in smaller chunks. There's specific goals for normalization. So when you're done the normalization process, you want to hit all 4 goals. Elimination of data redundancy. You don't want duplicated data. If you have duplicated data, it means you probably have to run really complicated update routines. Ensure data consistency. If your data isn't duplicated, it's easier to make sure it's consistent because you don't have to keep updating things like that. Simplification. Although some people look at a complex database structure with, hundreds of tables and say, oh, it's more complicated than looking at a flat Excel spreadsheet. But for the application developer, it's a way simpler when they only have to target one little thing instead of a big complicated data structure. Eliminate anomalies, and we're going to talk about anomalies in probably right next. Anomalies are bad things that happen to your data. And there's 3 kinds of anomalies. We have an insertion anomaly. So when you add data to the database, you add a new row of data, forces you to create duplicated data. When I start doing the examples, you'll see exactly what I'm talking about. But essentially, you're going to add new data to the database. You're forced to add duplicated data, such as, I don't know, countries or provinces or other things of that nature. Deletion anomaly. It's the opposite of the insertion anomaly. You delete a row of data and you may actually lose data, as in that the extra data that's tied to that record that really shouldn't be there just goes away, and since it's gone, it's gone. Update and modification anomaly. Changing the data in a row forces changes to other rows because it's duplicated. For example, if we are talking about a countries table, right? So we have a customer table and there's a country column. And in this country column, it's just a string where people put in values, right? Canada, US, Mexico, Canada, whatever. And then somebody decides to rename their country. Instead of changing it in one place, you end up having to update every single row where that data exists. So that's an update anomaly when you have to change the data more than once for something that really should only be one time. Changing the name of a country, that's a bit of an extreme example. But it is something for a while was happening really often in certain parts of Europe. Yugoslavia, for example, when Yugoslavia when turned into 4 countries. There's a couple of other Asian countries that have changed names 3 times in like 10 years. Having to go through the entire database to fix all that is not good. So normalization fixes your structure so that if you need to change the name of a country, you'd only need to change it in one place. Okay, so here's our first table of data. This is actually going to be talking about anomalies. And what's kind of cool about this slide is this example is from a textbook that I was using to teach a different course about 15 years ago. But that's not the cool part. The cool part is this exact same example when I went through school. It was the same textbook and they never changed this example. And I was doing normalization in 1995-ish, 94, 95. Somewhere around there is when I was learning normalization the first time, wondering why I ever needed to know it. Just saying. Every student has that thought. Why do I need to know this? Um, when I got a job in database, I then knew why I needed them. So we have a structure of data in here, and we have a bunch of issues with this data, this duplicated data. Um, for example, Marge Simpson right here is in here twice, two different salaries with the same salary, two courses, dates when they were completed. Um, Chris here, Susan. Um, there's also some unique values like this Alan Beaton person. It's the only one that has tax accounting, right? So let's go through some anomalies. Insertion. We can't add a new employee without having the employee take a class, or at least empty fields of a class information. So if I go back, when we add a new employee, we have to add a course. The stupid thing is, if the employee takes another course, we have to add the employee a second time also. So we end up repeating rows of data. We can only ever have one employee that didn't take any training. Lorenzo here, right? Because he's got blanks, but we can't really have another person with blanks. Well, we could. We could have one person with blanks as long as their name isn't repeated elsewhere. It gets a little wonky. Deletion. That's the example I use. If I get rid of Alan here, we discover Alan's been cooking the books a little bit and padding his wallet, and we fire him, we'll lose the fact that tax accounting was ever a course somebody could take. Update. So we're going to give Marge Simpson a raise. We need to update it in two places or more, because if Marge is like a busy bee and takes 5-6 courses, we have to update her salary 5-6 times. Now, with modern hardware, most of these updates are very, very fast. Like you blink and you miss it. Now, let's harken back to the dark old days, like even before I started doing computers, where data was stored on tape. I'm sure you guys have seen at least a movie where they had computers and the tapes are going back and forth, lights are blinking, and huge data center, and realistically, all the computing power in there is like, you know, a millionth of the power of my phone, kind of thing. 64K of RAM for the entire enterprise is enough. So picture this, where we have to update multiple rows of Marge Simpson, and it's on tape, and it updates the first row, the tape moves and the tape breaks, because that would happen more than you'd want it to know. Suddenly, Marge Simpson has two salaries because the update has failed. They patch the tape, then they copy the tape to something else, and now Marge has got two salaries. Maybe she's got $50,000 salary, and then a $48,000 salary. Which one's the correct salary? Maybe she got demoted. We don't know what her salary was. Obviously, there's probably paperwork to show it's supposed to be, but back then it was a real risk. Where I did my co-op, they were running an old IBM System 36. The computer part was a two of these desks. They were in the middle of working to move off of that. Just saying, it's so their main computing unit was twice the size of this desk, and the hard drive was about that big. It was in an enclosed room. You could feel the hard drive through the floor because it was really old equipment. We knew when something was wrong because the hard drive would stop spinning because it was dying. And you'd stop feeling the vibration on the floor. And that was one of us would then go into the server room and literally kick it. And the vibration would be enough to unstick it because the bearings were seizing. Yeah, again, what would happen if the disk stopped spinning while it was doing an update? Nowadays, everything's in solid state. It's like blink and it happens, but it's still a risk that, there's that chance that microsecond or that millisecond that your data will get toast. So why do these anomalies exist? It's because there's two entities in the same relation. So in this case, when we talk about a relation, we're talking about a table. And there's two entities in it. We have employees and courses. So those are the anomalies. The goal of normalization is to get rid of these by breaking things down to smaller pieces. Okay, so there's tons of normal forms. And at least they made it easy to remember. First, second, third. That's easy. Then there was fourth, and somebody realized they needed something in between. So it was literally two data scientists, Boyce and Codd, who came up with a solution. So it was called Boyce-Codd normal form. Many of us in the industry, we call it normal form 3.5, but the official name is Boyce-Codd. Fourth normal form, fifth normal form. There's actually higher normal forms. For 99% of database design, third normal form is all you need. Boyce-Codd is for edge cases. So this course, we're just going to concentrate on the first three. Because often when you're in third normal form, most of the time you're already in fourth and fifth. These are all designed to handle very specific edge cases. Um, Honestly, by the time you get to fifth, and if you actually hit that edge case, you are dealing with like NASA level data, not, you know, normal day-to-day data type stuff. And everything past that was basically somebody needed a way to do their dissertation for their PhD. Because in the cases for sixth normal form and some of the higher ones, and I have no idea how you'd even end up with data like that. So somebody came up and said, "Oh yeah, if we ever come up with this weird case this one time, this is how we solve it." Um, but realistically, first three are all we need. Okay. So a database usually is considered properly designed when it reaches third normal form. As I said, BCNF 4 and 5 exist to handle specific edge cases. I don't even remember what they are. We're going to do first three. So when we're doing normalization and writing it out, there is an accepted notation. It looks like the following. Entity name with attributes listed out in it with comma delimited. If you happen to be worrying about candidate keys during the normalization process, depending on what software you're using, it could be underlined, bolded, you know, italics, something to identify that this attribute's an identifier. Or if you happen to be working with really old systems, and I mean really old, you could bold a piece of text, or you're working in Notepad because you just like, you know, simplicity of Notepad. You can actually also say PK in parentheses or identify ID or whatever, just to mark, say that's the identifier. There's two notations you can use for this. Um, all right, so here's our normalization exercise. As you can tell, it looks just like the one from the other example because it's been around for so long. It does a good job explaining the concepts. All right, so we have a table of data. This looks like basically like a report of some sort, where we have an order with who ordered it and what they ordered. Then we have another order here with what was in that order. This is not even considered to be a proper relation because we have something called a repeating group of rows. And by repeating group of rows, I'm referring to this stuff right here. These guys are the repeating group of rows. So this chunk of data here has 3 rows tied to it. So it's known as a repeating group of rows because it's repeating values without necessarily repeating the entire row of data. So to be in first normal form, it has to meet certain criteria. A candidate key is defined. So we've identified how we're going to uniquely pull a record of data out of that table. There's no repeating groups of columns or repeating groups of rows. Multi-valued attributes are removed. The example doesn't have any of those. A multi-valued attribute would be a list of skills a person has. Right? You have multiple skills, one of you. When you're looking at this, you may end up with a column with comma delimited values. A common one you guys might recognize more would be phone numbers. You know, some of us have more than one phone number. So you'd have comma delimited phone numbers because that's multi-valued. There's a unique name for every attribute. So every column has a unique name of its own. So if we were to write this in the normalization syntax, it's right at the bottom of the slide. Order, opening square bracket. That is a bracket. So, you know, it's not parentheses or a brace, it's a bracket. Order date, customer ID, customer name, customer address. So if I go back here, so here's the first chunk right here. Now you'll notice that there is parentheses in here around product ID, description, finish, price, and quantity ordered. And then our closing repeating columns or repeating group of rows, whichever terminology, it's the same thing. So when we look at this, initially, nothing is identified as a primary key. Actually, that example has a primary key defined, but it's just unfortunate. But we have, this is the notation for repeating columns or repeating group of rows. Yes, we're going to get to that in a second. That's next. So how do we fix this to turn it into a proper entity? It's easy. We just fill out the entire row. So by taking this first piece up here and just copying it down, taking this piece and copying it down so that every row is complete, we got rid of the repeating group of columns because now each row is complete unto itself. It's not a part of the row depending on something else. The whole row is complete unto itself. Okay, so that's the first thing. And our candidate key in this happens to be order ID and product ID. How did we pick it? Those two attributes combined allows us to find any given row. So 1006, 7, well, that's that row. 1007 and 11, well, that's that row. 1007 and 4, cool beans, we can find that row. 1006 and 4, we can also find that row. So we can ignore these strings because this is the candidate key. Now, when you're deciding on a candidate key, you are trying to find the minimum, the least number of rows, the minimum number, number of columns, the least number of columns that allows you to identify a row uniquely. You want less is more in this case. So you want as few columns as possible in your candidate key. So you keep eliminating everything else until you have something that's unique. Now, in here we have repeated dates, but the dates match this number, this matches that. So these guys match this because that's how it was organized originally. These numbers are repeated, but the combination of order ID and product ID is not repeated. It can be just one column, it could be two, could be four. In this case, yes, it's a composite key. So last semester, you guys learned about primary keys and composite keys, I'm assuming, since you just brought it up. At least when I taught the level one course, I did talk about them really quickly, knowing you guys are getting a way thicker version of it in this. But yes, this is a composite key where two attributes combined allows you to find a given row in it. So at this point, we've identified our candidate key. We got rid of the repeating group of columns. We can say that this table is now in first normal form. We still have all these anomalies, but at least it's in first normal form, as in we can retrieve a row of data out of this table. If we're unable to retrieve a unique row of data, it's not in first normal form. That means there's something wrong. If we can retrieve a single row by providing specific criteria, it's in first normal form. We still have the anomalies. For example, product ID 4 is repeated. The customer information is repeated. Those anomalies are still there. So if we were to write this in the proper syntax, we'd go order ID is underlined, product ID is underlined, and you'll notice we just took away the parentheses. So when we're getting away from the data and just looking at the attributes, just getting rid of the parentheses magically fixes it. Literally, this case is just a syntax erase, fixes the problem. But yeah, second normal form. To be in second normal form, you must be first in first normal form. It's possible to be in second normal form unless you're in first normal form. End of story. Do not pass go. You can't be Super Saiyan unless you're Saiyan first, depending on which example you want to use. Every non-key attribute is fully functional dependent on the entire primary key, which means there's no partial dependencies, partial functional dependencies. So remember all those definitions I was doing at the start of class? This is where these come home to roost. So when we go over back to this table, Right here, we look at the dependencies. All right, order date is fully dependent on the order ID. Cool beans. Customer ID, dependent on the order ID. Customer name and address, also dependent on the order ID for now. Product description, finish, and price, they're all dependent on the product because that's, defines the product. The quantity ordered is dependent on the order ID and the product ID combined. To find this value, you have to give it both of these. But to find the value of the product description, you only need the product ID. You don't need the whole row. So these are partial functional dependencies. So, so no, the order date, customer number, name, and address is dependent on the order ID. The description, finish, and price is part of product ID. The quantity is part of order ID and product ID. So that's the breakdown of these entities. And of course, when I did these slides, I didn't write it the right format, but So if we were to write it in the correct format, yes, apparently I did fix it last semester. The last semester I taught this. It's going to look like this. So we took that big long entity we had and we decomposed it into 3 pieces. So we made 3 smaller pieces. We have order, which is the ID, the date, the customer information, the product, which is the product ID, description, finish, and price. And then we have the order line, which is the product ID, the order ID, and how many was ordered. So at this point, if we need to update anything, we only need to do it for now in one place. There is still a problem. That's why it's only second and not third normal form. Now, this is in third normal form. This one's in third normal form. Order is not in third normal form, and we're going to discuss that in a moment. But essentially, if we have a product, so if I go back to my list of things here, so product 7, it's a dining table that's ash that sells for $800. Man, this is really old slides because a net table nowadays will cost you like $4,000. Wood's really expensive. But in this case, or 4 is a good example, right? Because right now in here it's repeated twice. So if we wanted to change the price on this entertainment center, we'd have to change it in 2 places, right? But with this structure, we only need to change it in 1 place because it's product ID 4. We change 1 entry for 4, and it doesn't affect what's been ordered. So that's rewriting it out. So to be in third normal form, you must be in second normal form. Surprise. Like that was the surprise of the day, right? The shocker. Transitive dependencies are removed. Now, what is a transitive? It's when an attribute can be identified as a transitive when it's determined by another attribute that is not part of the candidate key. Okay? So relation R has attributes A, B, and C. A determines B, and B determines C, therefore A determines C, correct? But what happens if A doesn't determine C? That B determines C. So if we go over here and we look at this, we have customer ID, customer name, customer address. The name is actually dependent on the customer ID. But because we didn't need to include the customer ID in the candidate key, we didn't get rid of it as a partial dependency. It's a transitive dependency. Order ID determines customer ID determines name. So we have to transit through customer ID, thus it's transitive. And anybody want to take a guess how you fix that problem? What did we do to fix the first problem? We broke it down in smaller pieces. Therefore, how are we going to fix this problem? We're going to break it down in smaller pieces. That's what we're going to do. So right now in the order is right here, right? So address and name is dependent on the customer ID. The customer ID is determined by order ID. So realistically, these are the 2 relationships. Customer ID is not part of the candidate key. So it can be said that order ID is determining the name and the address because it's transitive. And how do we fix it? Break it down into yet it's another component. So we create a customer. It has a customer ID, the name and the address. That means now that if a customer moves, we only ever need to change their address in 1 place once. With the structure we had before, We might have to, for every order they placed, for every item they ever bought, we'd have to update their address. That'd be awful. In order, we keep the customer ID because we need to know who bought it. And since customer ID is determined by order ID in the order table, keep it. So the big difference between partial and transitives is partials, you take the whole thing lock, stock, and barrel and you just move it out. Transitives is you take it, you make a copy of it and get rid of anything that's not determined by the candidate key. So in the end, we have 4 nice little tables. In the end, there'll be tables, which we have a customer ID, customer name, address, ID with date and customer, and these ones we discussed ad nauseum. So to discuss the goals, first normal form, atomic values, no repeating groups, means it eliminates multi-value attributes and repeating groups of columns. Second normal form means it's in first normal form and all the columns are dependent on the primary key of the candidate key. We get rid of partial dependencies. Third normal form, it's in second normal form. There's no transitive dependencies. What we're getting rid of is literally that. Okay, now we have another example, and I did something stupid today. I forgot to grab all my good markers. I have a whole bag of like rainbow colored markers, and I usually color code everything I do. I'm going to do this example today as is. I'm probably going to be doing another example later this semester, but basically the week before the midterm, so that we do the whole thing. Because with that example, I'm going to do in like 3 weeks from now, 3.5 or 4 weeks. I cover not just normalization, I do the diagramming. So I start from this and I finish with diagrams. But for now, I'm going to do this. So I can write right on it without writing on the screen. Okay. Oh, we have the font small, I know. But this, you can picture this as um, a library database where you receive a dump of data from the library. Everything is on it. Now, when we look at this, how do we find a unique row of data? So that's the first thing we have to do, right? The good news is I was really kind and I didn't do repeating groups of columns, so you don't have to worry about eliminating that problem. But in here, um, what combination of attributes lets us find a unique row? What was that? Because yes, whoever said borrow ID, because right now we have this one's repeated, and Catcher in the Rye and the author ID because the Catcher in the Rye is written by the same author. So yes. So what we have is and the borrower ID. That is our. Don't tell me this marker is going to die. It's just going to go with the rest of my day. So that's our the key. So now what I'm going to do is I'm going to write it out here, turn off the screen, and then we're going to work across the board with apparently one color. No, I didn't leave my other marker upstairs, did I? Okay. So I'm going to write it out over here. I'm going to do it in blue because I think my black is dying. And then I'm going to turn on the light and turn off the screen. So we have, let's call this library. And we have book ID, which we know is a candidate key. Book title, author ID, author name, uh, genre name. Actually, should have been a capital N, but anyways. Borrower ID, which we've said already. Borrower name. We're almost done. Borrow date. Return date. Great. So this is the text version of that. Now, before I turn off the screen, let's try to identify what's dependent on what. Okay, so let's start with the borrower is the easy one. The borrower name only belongs to the borrower, right? Because the borrow date is not just the borrower because we're talking about a book, right? So there's more. Author ID, author name, and genre ID and genre name, they're not participating in the key pool, but they have nothing to do with the borrower ID, and they also have nothing to do with when the book was borrowed. So this whole set is dependent on this piece. And in the end, we have our borrow date and return date, which of course I'm writing green on green. That's a great idea. Is dependent on the entire candidate key, like such. Sorry about the green on green, folks. So we know that this is dependent on the whole key, this is dependent on part of the key, and this is dependent on part of the key. So this is a partial dependency. This is a partial dependency. This is a full dependency. So how many entities am I going to break this down into? 3 starters. Okay, now turn that on. Oh, that was bright. Turn this off. And now we just got lines. It's a good thing I've done this enough that I remember all of this. Essentially, if I go and do this, now that the screen's not in the way, and I just go like, we now just so happen to be broken down exactly the way it ended up being almost. Okay, so somebody was really serious about cleaning the board. It's a magic eraser. Okay, so if we take this piece here and we're going to break it down on that board, not sure how far my camera grabs, at least that side of the screen. So we'll do, yeah, we'll do it over here. Uh, blue marker, because that one's working. So if we do book, which we have the book ID, and I'm going to start dropping words I don't need here, just save on writing. Title, author, ID, author, name, genre, ID, genre, name, like such. That's its candidate key. We have a borrower, which we have the borrower ID and name. And then I don't know what I'm going to call this table. Lend, I guess, for lack of a better word. And in here, we are going to have the book ID, the ID, the borrow date, and the return date. And wrong thing, like that. And this is the candidate key. Now here, what I'll do is I'll put in another underline in a different color. Um, Normally you don't do that, but it's just for me to show you guys something. Although these are participating in this candidate key, their values are being defined. They're foreign keys. So remember foreign keys from last semester when you did a join, primary key to foreign key? These are, this is a compound primary key where the members get their values from their parent tables. So that's why there's the green underline. Okay. All right. Now, usually people take pictures of the board because I'm going to erase this board in a second. So if anybody wants to take a picture of the board, here's your chance. Because I also can't guarantee that I caught that. That I'm not going to erase right away. But okay, everybody's good? Okay, excellent. Yep. No, no, the book and borrow ID is the candidate key. Lend is the name of the entity or the table in the end. It'll be a table in the end. So I called it lend because I don't know what to call the table in a library system that says, these are the books people borrowed, you know, because you're lending out stuff. I know there's a technical name for it and I just don't remember what it is. And I've been using this example for years and I had one year where I had a student that was a librarian that actually said the right word. And I just don't remember what it's called. Um, so it's the best part of keys. It's a composite primary key that are foreign keys. It's an everything key. Literally, this key right here is everything in one. So if I think I remember level one, there's a slide talks about how an attribute can be a key, can be a foreign key, can be a composite key, can be a combination of any of the above. This example, it's all of the above. So these are attributes that are a candidate key. It's a composite key because there's more than one. And they're foreign keys because their values are coming from up there. This is known as a weak entity. I'm going to be talking about, actually I talked about weak entities last week. You can't lend a book unless you have a borrower and a book. So this row can't exist without these guys up here. That's why it's weak and it's foreign keys that participate in a primary key. That's composite. It's an everything key. It's the best kind of example. I hate those, by the way. In the real world, I don't do these when I make database designs, just so you know. I find another solution than that because they're a pain in the butt. Especially when you start getting a really complicated table where you have 4 or 5 keys going into a composite key, it's really gross. Okay, so I'm going to erase this bit like such. I'll get points to the magic eraser. It does a really good job. Um, so if we come over here, I'm going to use my black marker because I've already got the other colors. This one here is in third normal form. Why is it in third normal form? The name is dependent on the borrower ID. There's nothing transitive. So every non-key attribute is fully dependent on the key or the candidate key. Same thing here. These two are dependent on the entire key. Neither of these is determined by part of the key, and there's nothing transitive. So this one's already in third normal form also. This one's in second normal form. Why? Because there's two transitives. The book ID doesn't determine the author's name. The author ID determines the author's name. Therefore, book ID determines author, which determines name. Therefore, book ID determines name. It's a transitive because it transits through another one. So this one's transitive. Such. And the genre name is the same situation. It determines the genre ID. It's these two, we have two transitives. If I wanted to make this simpler, I could have just gotten rid of the genre table and it'd be the exact same thing. Sometimes it's good to see a couple of transitives at once. So how do we fix this problem? We break it down into smaller pieces. All right, we have book. Actually, let's go in the order of dependencies here. So we've got author, we have genre, we have book, we have borrower, and then we have lend. All right, so here's our 5 entities. Now I'm just going to fill them out. Over there, we said the author name is determined by the author ID. So that's basically our 2 attributes. So we have author ID, and I'm just going to say name at this point because that's fine. There's only one in here. And we know that the author ID is the candidate key. Cool beans. We have a genre. Again, here we have the genre ID. ID and name. And again, nice and simple. The book. We have the primary key. We have the title. We have the author ID and the genre ID. And I'm going to break out my little green marker so that you guys can see that this is a foreign key, like such. We had our borrower, which and name, and then we have the entity, which was this one stays the same too because nothing's changed. Book ID, borrower ID, uh, borrow date, return date, primary key happens to also be foreign key. And at this point, it's fully normalized. If we need to change the name of a borrower, we only need to change it here. An author changes names for whatever reason. We entered it wrong the first time. We need to fix it. We only need to change it here. We don't need to change it 5 times, 6 times, 10 times for each copy of the book. In theory, you could have multiple copies of the same book, right? Most libraries don't have just one copy of each book. They have multiple copies of, especially when it releases. But if we need to change the name of the book or adjust the genre of the book, we only need to change the name of the genre or adjust the genre in one place. So we ever need to change something in one place. That's before you even create tables. This is the design phase where you're making sure your data is sane. There are still issues with this structure, but we only do third normal form, which is all. Realistically, in here, we actually do have one last anomaly, which is the author and the genre ID. Because realistically, if you have multiple copies of a book and we need to change it, we'd have to change that value on all the copies of the book. But for a third normal form, this is correct. What we'd end up doing is if we wanted to only ever have to change it in one place, actually it'd be a real pain in the ass, to tell you the truth. We'd need 3 more tables, fix it. Past this. We would need a book ID that identifies a given book, so Catcher in the Rye. Then we'd have to have a copies table that shows each of the copies of the book we have. And then the book table would have a many-to-many association with the genre and the authors, so that we only ever need to change the association in one place, but a book could have multiple authors, because you guys have seen your textbooks, right? 3, 4, 5 authors on the textbook, even realistically there's only one guy and all the other ones are just ones updating the textbook after it was created. So this one here is still a big problem, realistically. Honestly, for third normal form, this is good enough. Like I said, if I wanted to fix this problem, I would have to go much further than this. Because, like I said, I have to have a book table, I'd have to have a copies table, which means our lend table would change, because it wouldn't be the book ID anymore, it'd be the copy ID. And then we'd have another something else. If we just want to have one author and one genre, we could leave it like this, and we just need a copies entry outside of that. So there's 2 or 3 ways to fix this problem, which is good. And I forgot to put myself on Do Not Disturb. You know, I make fun of students when they do this, and I forget to do it myself. Usually students, the phone's ringing, like it's calling, not just dinging. Okay, so this is the normalization process. Did you want me to show you the next solution for this? So take a picture of this, and I'll go one step past this, and I'll fix the book, the lend, and the lend, so that we only ever need to change the thing in one place. So if you want a picture of this the official final solution. Now, if I want to fix this, I'm not going to redo all the tables. My handwriting is bad enough. But if I wanted to fix that issue where if I want to change the author or the genre of a book, and we have multiple copies of the book, how would we fix that? We would do it by having a book table. So we go, book would stay exactly the same. That's the cute trick, right? So we got book ID, title, so how you write title, genre ID, and author ID. And I know I have them in the wrong order, really doesn't make a difference. Like this. All right, and then we have our lend down here. And the issue we have is right now, if we have multiple copies of the same book and we need to change the author, whatever, we end up having to update multiple rows, even though it's in third normal form. This is literally what Boyce Cod is for, is to handle this situation. So it's the next one out. So what we'd have something probably called copies. Because often at the libraries, when they have more than one book, they call it copies of the book. And in here, we'd have a copy ID and the book ID. Copy ID is a primary key. Book ID is the foreign key. And the lend now, instead of being book ID, we'd have copy ID, borrower ID, borrow date, return date, like such, and primary key. Foreign key, and that's how you fix that problem. So what we're doing is resolving something that's not a third normal form issue. We're resolving I don't remember if it's Boyce Cod or fourth normal form. This example, when I created this example, I made sure that there was like all kinds of room to grow with the example past just basic third normal form. So to get rid of this, we end up having to fix this problem, even though we technically have no problem. It's just instead of having just one copy of the book, we have 3, 4 copies of the book, and they'd all have their unique book ID. But then we'd have to update multiple rows. This lets us have one book, multiple copies of the book, and people borrow the copies, not the book itself. So that's the fix to this. No, no. So the book has multiple copies. Each copy is only of one book. So if we remember, I talked about one to many, many to many last week. This is a one to many, and this is one to many this way. So Catcher in the Rye is the book. We have 3 copies on the shelf of Catcher in the Rye. But we only have one Catcher in the Rye, but 3 copies of Catcher in the Rye. So therefore, the relationship doesn't go this way; it goes that way. And people borrow each of the copies. And a person, more than one person can borrow the same copy because I borrow it, return it, somebody else borrows it, they return it. Therefore, the borrower returns the whole thing. And even this, and this has problems too. But because think about it for a second. How many of you have actually borrowed books from a library? Okay, good. Just every year that number gets smaller. How many of you have gone to a library and actually walked out with a book in your hand? Not me. Um, Sometimes you borrow a book and you're really busy and you didn't have a chance to finish it. Or, you decide to borrow a book and you didn't realize how thick it was. Robert Jordan's books, The Wheel of Time, 1,000 pages of book and there's 14 books. It's going to take you a while to get through all those books. And you've got a busy school schedule and you don't have time to read a 1,000-page book in a month. Therefore, you go and you renew. So now what, do we have to change these values? Or do we do a new entry for the person? And then suddenly what happens if, we borrow the same copy multiple times? Now we need to have something else, This is where, the whole database design thing suddenly just goes down a big giant rabbit hole as you think of possibilities. But when you do normalization, you're not supposed to think about the possibilities. Like this was not part of the normalization process. Like this was not part of that initial normalization process. This was me identifying a problem and fixing it from experience. When you're doing normalization in the beginning, you should only work with the data you're given. So when you guys go to do lab 3, yes, lab 3, only work with the data you're given. Don't create new data. Don't try to come up with alternate solutions. When you submit the work, you're literally going to give it to me like first normal form written out, second normal form written out like I did, third normal form like I wrote it out. That's the submission, at least from what I remember of the lab being. But yeah. If you are wanting more examples of this, I hate to say it, ChatGPT and Copilot does a great job coming up with examples. And best part is you can ask it for an example and then show you how to solve it, and it'll give you a nice explanation. How do I know? I've had to put myself, pretend I'm a student and ask stupid questions of ChatGPT or Copilot. From my experience, Copilot's a little better for this. Don't know why. Because usually Copilot's worse. But it's actually pretty good at this kind of stuff. So if you're asking for examples on how to expand on it, Copilot's your go-to on this one. You can just ask it a quick question of, hey, can you give me an example of normalization that includes partial and transitive dependencies? And can you provide the solution? And it'll actually show you how to break it down. And when you do it, it'll go past that. Last time I did, it actually gave me the SQL scripts to create the tables from the examples. They went all the way, no diagram, but it went from raw unnormalized data to create table commands. So it's kind of cool, But yeah, so this is normalization. That was literally the last slide of the night. That is the content. it is a chunk of information. It's a hard one to. The funny thing is about normalization is either you can spend 4 weeks on it or spend an hour and a bit. There's no in between. Um, Realistically, this covers everything you need to know about it. Don't forget to do there's a hybrid that goes with it. Hybrid 2, pretty sure, is a normalization hybrid. Um, and just so you know, I don't care if the hybrids are late by a day or two. They're there, get them done like within the week, and I'm happy. So don't panic if you're a couple of days late or your laptop died or whatever. Um, I don't really care. I don't look at the hybrids are self-grading, so I don't even look at them. I just make them go away after like you know too long, so you can't do it late, super late. All right. So does anybody have any questions? Yeah, it's due Sunday. As I usually don't release the okay, so unless everybody has submitted, I don't release the grades till after the due date. Historically, I used to give people grades right away, and then I discovered that after the first 4 or 5 people, the answers started looking awful similar. I'm like, well, of course they are. So the eager beavers went and did it first, and then everybody's copying off them. So the grades will be published usually within a. Technically, we have 7 working days from the due date. I try to have it within a day or two of the due date. I usually spend my Sunday. Basically, most of it's graded right now. It's just a few people hadn't submitted their lab 1 yet. When after I turn off the recording and stuff, I will probably go check, see if everybody else has submitted, and then if everybody has submitted, I'll just publish the changes of the grades right now. It's just I won't publish until either everybody has submitted or the due date has come and passed. I will publish the grades even for people that are late, that taking advantage of the 1 week grace period, because they're going to lose points no matter what. So I don't really care at that point. All right. Any other questions? Clear as mud? Absolutely. All right. Okay, you have a question related to this? Absolutely. So realistically, with normalization, you will be receiving a huge pile of raw data. And it's kind of funny because before I started working at Health Canada, I never thought it's so rare that I saw normalization. I was thinking it was like a dying skill, right? Then I was helping somebody because Health Canada and the Public Health Agency of Canada, they're sister organizations. Like they even share the same office and the same infrastructure. Like they're on the same network. And we happened to have a data scientist who was having a hard time with his data. And my manager, knowing me, knowing how well I know the stuff, she made me go down 2 floors and walk halfway across the building, go talk to this person to help him. And he was given flat files coming from collection systems. So, for example, when somebody gets a vaccine and there's an adverse reaction, this is actually the data set. The pharmacy, so for example, you went to the pharmacy and you got your COVID shot. You've had it, 5 times before, never had a reaction. This time you get the shot and you have a bad reaction. The pharmacist not only gives you, the epinephrine or whatever, the EpiPen to make sure you don't die on the floor and call an ambulance, they have to report that something happened. All this data lands into a system and it came out as big flat tables of, pharmacy, vaccine, reaction, patient, blah, blah, blah. And there was like millions of rows. And the problem was the millions of rows wasn't just adverse, it was every shot, whether it was adverse or not. So then I helped him break down his data because he was having a hard time breaking down his data. So that turned into proper tables that were then reported upon. But yes, you'll get a table of data, but it might not come as a table in MySQL or in Postgres or Oracle. It might show up as a giant CSV file or as a Parquet file or some special format. You take the raw data and break it down into sane pieces that can then be broken down into a database for reporting purposes. Okay, any other questions? Going once, twice, 2.5 time? 3, sold. And now I'm going to stop the recording. So that having been said, and